integer solution to this congruence. And what I mean by that is we're looking for an x that is between 0 and let's 78. Because when you divide by 79, your biggest remainder is 78. For that reason, modular arithmetic is sometimes called congruence arithmetic. Okay. So again, we're looking for an x that satisfies this. Now, yeah, you can check too. If you tried x equals 2, let's just so you get a feel. If you're not familiar with the congruence arithmetic, x equals 2 would give us 90. All right. But 90 is not congruent to 13. And that's because 90 minus 13 is 77. It's close, but it's not. 90 minus 13 is 77, right? So, but the difference would have to be a multiple of 79, and it's not, okay? So, and again, you can try some other values, but the large modulus and the relatively large coefficients make it hard to guess and test here. So we're going to try this interesting approach that kind of parallels multiplicative inverses just with regular real numbers. Now, y'all, what I mean by multiplicative inverse is something like this. Let's say 45. And y'all, I'm going to write down capital I. Don't confuse it with a 1. It stands for inverse. And I'll make sure and do something very prominent like that. Now, so we got 45i must be congruent to 1. And I'll write mod 79. Now, sometimes you can just see it for smaller numbers. Many times, even competition level problems, you can see this. But right here, it's not so hard, right? I mean, look, we just tried 2. You can experiment with some smaller integers, and you're not going to have any luck finding it. Okay, I know because I designed the problem. So this I is called the multiplicative inverse because when you multiply I times 45, you get 1, okay? And y'all notice this is similar just to, like, say 5/3 times 3/5. This is obvious and kind of trivial here, but 5/3 times 3/5, they're multiplicative inverses. They're multiplicative inverses because they equal 1, right? It's the same thing here, but it's slightly more complicated. I mean, it's the same structural thing. It's a number such when you multiply it by the number of interest, you get 1, but it's in the modulus world. Okay. Now, again, sometimes you can guess and test, but in this is not one of those instances. Now, y'all, this step you see here is called the Euclidean algorithm. I think Euclidean algorithm. We're trying to get 1 in terms of 45 and 79, meaning we want to get it as a linear combination because once we do that, we can actually read off the inverse pretty quickly. All right. Now, again, all this work I'm not going to go through. This is all pretty straightforward right here. The part that's rather tedious is this back substitution stage right here. See what you can just follow along the steps. You see what I did right here? I wrote down that 1 is equal to something that's obvious, 34 minus 3 times 11. But you're not interested in doing a computation here. Now notice that 11 is equal to 45 minus 34. That's where this 45 minus 34 comes from. And we're trying to get to a point where it's a linear combination of 45. And it's connected all the way to the back, basically. All right. And so all of this work gets us to this step. And you guys can verify right here. But all of this work, remember 1 started out and we had this chain of equalities. And I double-checked the arithmetic. I'm pretty sure it's all right. Now, this is equivalent to this statement, okay? This equality right here is equivalent to this statement. What it says is that minus 7 times 45 minus 1 is a multiple of 79, which is exactly what this says up here, okay? If you look at it and just get stuff on the correct side, it'll be, if you bring this to the other side and bring this to this side, that's the equality that would induce this congruence. But you see, we have our multiplicative inverse here. That would say that minus 7 is equal to our I. Okay? Now, why is that important? Because minus 7 times this in the modulus world is 1. Okay? So let's come back up to the original problem. Now, y'all, and I'll just write it. This is kind of sloppy, but I'll write. When you multiply this side by minus 7, you actually get, and I'll write down 1x for emphasis. Okay? Now when you multiply this by, and it should be negative 7, folks, you get minus 91 right here. Now that's a solution. It's just not in this so-called reduced residue system. Okay, y'all, again, I hope you see the work there. Since my writing on this thing's a little cumbersome, I leave stuff out. But if you multiply 45 by negative 7, that's congruent to 1. It's equal to 1 modulo 79. Minus 7 times 45 is congruent to 1. We've shown that with this tedious work right here. Okay, so that's what happened right here. We multiplied this by minus 7. It became 1. Minus 7 times 13 is the real deal here. Now we want to get a number between 0 and 78. Now this would be congruent to negative 12, right? Y'all just think of positive integers. 91 minus 12 is 79, right? Okay, but notice, so they're separated by multiples of 79. Now, so the one we would be interested in right here would be 67. Notice that 67 and minus 12 are separated by 9. 67 minus a negative 12, if you must say it that way, is a multiple of 79. Okay, and again, you could keep adding multiples of 79 all the way out. But we are interested in an answer between 0 and 78. So this is our answer right here, 78. Or this is our answer, 67. Okay, that's the answer, ladies and gentlemen. X is equal to 67. Okay, so that's the problem, folks. And again, let me know if you know an easier way to do it, but I think this is the best way. A lot of the textbook problems don't have these bigger constants, and you can kind of guess and test what the multiplicative inverse is, you know. But this is not one where you're going to guess and test the multiplicative inverse. Okay. So in any event, this is the solution to the problem. And again, you can verify it. Check it out. 45 times 67, you'd probably need a calculator. You can do it by hand if you have to. But 45 times 67 minus 13 will be a multiple of 79. Okay, thanks for viewing.